That massive sheet of dark, luxurious glass spanning across the roof of your modern vehicle is not an engineering achievement. It is a structural, thermal, and electrical liability designed to make a vehicle look expensive on a showroom floor while quietly creating a cascade of long-term mechanical failures. For decades, the steel roof of an automobile served a fundamental purpose. It was the primary structural cross-brace of the unibody chassis, acting as an indestructible shear panel that absorbed torsional twisting and provided an impermeable barrier against environmental elements. Replacing hundreds of square inches of stamped high-strength steel with a heavy, rigid piece of tempered glass permanently alters the structural integrity of your car, introduces catastrophic failure points into your vehicle's sensitive electrical network, and subjects the glass itself to microscopic physical forces that cause it to shatter spontaneously without a single touch. To understand why panoramic sunroofs are turning into a financial nightmare for vehicle owners, we first have to look at the violent physics happening at a microscopic level inside the glass itself. Panoramic roofs are made almost exclusively of toughened or tempered safety glass. To manufacture tempered glass, raw float glass is heated to over 1,200 degrees Fahrenheit and then rapidly cooled using high-pressure air jets. This extreme temperature manipulation forces the outer surfaces of the glass into intense compression, while the inner core remains locked under permanent tension. This stored mechanical tension is what gives tempered glass its structural strength, until that delicate internal force balance is disrupted. During the chemical production of float glass, trace elements of nickel and sulfur inevitably combine to form microscopic impurities known as nickel sulfide inclusions. These inclusions are virtually invisible to the naked eye, measuring less than 1/10 of a millimeter across. However, nickel sulfide possesses a unique and dangerous physical property. It undergoes a phase transformation over time. When heated during the tempering process, these inclusions shrink into an unstable phase, but as the glass sits exposed to the sun over months or years, those nickel sulfide particles slowly expand in volume by up to 4%. Because the core of tempered glass is under extreme permanent tension, the 4% expansion of a single microscopic particle acts as a point source wedge inside the glass structure. The second the internal stress exceeds the shear strength of the material, the entire stored tension releases instantly. The result is a violent, spontaneous explosion that sounds like a shotgun blast inside the cabin, showering passengers in thousands of cubic fragments of glass at highway speeds without any prior external impact. This is not a theoretical anomaly. It is a documented manufacturing reality that has triggered massive class action lawsuits against major global automakers. But spontaneous glass fragmentation is only the first layer of this structural compromise. The second, far more systemic problem lies in the fundamental mechanical engineering of the vehicle's unibody chassis. A modern unibody automobile does not rely on a separate heavy steel frame beneath the floorboards. Instead, the entire outer shell of the vehicle acts as a unified load-bearing structure. When you drive over a speed bump diagonally, enter a steep driveway, or take a sharp corner at high speeds, the chassis experiences intense torsional flex. The front suspension pillars twist in one direction while the rear structure resists, sending severe diagonal shear forces through the A, B, and C pillars directly into the roof structure. In a traditional vehicle, a stamped steel roof panel welded directly to the body pillars absorbs this torsional energy smoothly, flexing slightly within its elastic deformation limit before returning to its original shape. Glass, however, possesses virtually zero elastic deformation capability under shear stress. When you cut out the structural steel roof and bolt in a massive panoramic glass assembly, you create a structural void in the upper frame of the vehicle. To prevent the entire car from feeling loose and unstable, engineers are forced to add heavy steel reinforcement beams along the perimeter rails and floor pans, adding 30 to over 100 pounds of dead weight at the absolute worst mechanical location possible, the highest physical point of the vehicle. Adding heavy mass to the roof dramatically raises the vehicle's center of gravity, increasing body roll in corners, and placing higher dynamic loads on the suspension bushings and anti-roll bars. But even with heavy perimeter reinforcements, those structural perimeter rails still flex during normal driving. Every time your vehicle twists over an uneven road, that movement transfers microscopic flexing loads directly into the rubber seals and aluminum tracks holding the panoramic glass. Over tens of thousands of miles, this continuous mechanical stress fatigue weakens the structural urethane adhesives, misaligns the heavy mechanical drive tracks, and places continuous perimeter pressure on the edges of the tempered glass, the exact location where tempered glass is most vulnerable to catastrophic stress fractures. While mechanical chassis flex slowly degrades the physical mounting of the roof, thermal expansion creates an entirely different daily battle inside the cabin. A standard sheet of body steel has a specific thermal expansion coefficient, expanding and contracting predictably with ambient temperature changes, whereas glass and aluminum tracks expand at radically different rates than the surrounding steel frame. On a hot summer day, a panoramic glass panel exposed to direct sunlight can easily reach surface temperatures exceeding 180 degrees Fahrenheit. As the glass expands within its tight structural cavity, the rubber weather stripping designed to seal the unit is subjected to extreme thermal compression and ultraviolet radiation breakdown. The continuous exposure to UV rays bakes the flexible synthetic rubber, causing it to lose its elastomeric properties, harden, shrink, and form microgaps around the perimeter of the frame. This brings us to the most common, economically devastating failure mode of every panoramic roof system: water drainage failure. Automotive engineers know that no rubber seal, regardless of how well it is designed, can remain completely watertight against heavy rain or high-pressure car washes over a 10-year lifespan. Because of this physical reality, every panoramic sunroof is built with an internal water catch basin, a hidden plastic or aluminum gutter channel running beneath the perimeter of the glass frame. When water bypasses the outer rubber seal, it drips into this internal gutter, which then routes the water through 4 small flexible plastic tubes running down through the interior A-pillars and C-pillars to discharge safely onto the ground beneath the chassis. This design functions adequately on a brand new vehicle leaving the factory floor, but in the real world, those 4 internal drain tubes represent an inevitable point of total system failure. The entry ports for these drain lines are tiny, often no larger than the diameter of a standard pencil. As wind blows over the vehicle, dust, tree pollen, organic debris, and road grime wash directly past the aging rubber seals and settle into the internal drain gutters. This slurry mixes with rain water to create a dense, organic sludge that flows directly into the drain tubes. Over time, this sludge accumulates at the bottom exit valves of the drain lines, which are often equipped with restrictive rubber check valves designed to prevent road noise and insects from entering the cabin. The sludge hardens, completely clogging the drain line. The next time your vehicle is parked outside during a heavy rainstorm, the internal water catch basin fills to capacity in minutes. Once the gutter overflows, gravity takes over, and water begins its path of destruction through the interior of your vehicle. The overflowing water does not just stain the fabric of your roof headliner. It flows silently down the inside of the hollow steel body pillars, directly behind the interior trim panels. Modern vehicles route critical, high-density electrical wiring harnesses and sensitive electronic control modules directly through these exact pillar channels. As water cascades down the A-pillar, it saturates the factory wiring looms, filling multi-pin electrical connectors with standing water. Even worse, automakers frequently mount critical electronic control units, such as the body control module, the audio amplifier, and main fuse blocks, directly in the footwells beneath the carpet or behind the lower kick panels. When the sunroof drains overflow, water accumulates quietly under the synthetic foam backing of the floor carpet, completely submerging these multi-thousand-dollar electronic components in standing water for days or weeks before the driver ever notices a wet floor mat. The result is immediate, severe galvanic corrosion inside the electronic control units. The electrical current flowing through the waterlogged pins causes rapid pin corrosion, green copper oxide buildup, and short circuits across sensitive circuit boards. Suddenly, a vehicle owner experiences bizarre electrical anomalies: power windows operating on their own, instrument clusters flickering, doors refusing to unlock, engine no-start conditions, or complete vehicle network failure. Mechanics spend dozens of hours chasing ghost electrical diagnostic codes, only to discover that a clogged 5-cent rubber drain tube has ruined $3,000 worth of submerged electronic control modules. Furthermore, fixing a broken panoramic sunroof mechanism itself is one of the most labor-intensive procedures in modern automotive repair. Because the dual-panel glass assemblies are heavy and complex, they rely on long, flexible drive cables, plastic guide shoes, and electric stepping motors to tilt and slide the heavy panels. The plastic guide shoes, made of nylon compounds, are constantly subjected to high heat under the glass roof, causing the factory lubricating grease to dry up and turn into a sticky paste mixed with airborne dirt. When the driver presses the switch to open the roof, the electric motor forces the dry cable against the brittle plastic guide. The guide snaps, jumping the cable off its track and causing the heavy glass panel to jam at a crooked angle. To replace a simple snapped $10 plastic track guide, a technician cannot simply unbolt the piece from above. The entire interior of the vehicle must be disassembled. The interior seats often have to be removed, all pillar trim panels unclipped, grab handles unbolted, and the entire molded headliner delicately lowered out through the rear door of the car without creasing the material. Only then can the heavy, 100-pound panoramic cassette frame be unbolted from the bare metal chassis roof and removed from the vehicle. The labor time required for this teardown frequently exceeds 8 to 10 shop hours, turning a minor mechanical component failure into a $2,000 to $3,000 repair bill. Ultimately, the panoramic sunroof is a textbook example of modern automotive engineering sacrificing long-term physical durability, chassis rigidity, and electrical isolation for short-term aesthetic appeal. It replaces structural steel with heavy, unpredictable tempered glass under extreme internal stress. It introduces complex mechanical drive systems into a high-vibration environment and relies on delicate, micro-scale drainage paths running directly above thousands of dollars of sensitive interior electronics. When you buy a vehicle with a panoramic glass roof, you are not simply choosing a luxury option that lets in natural light. You are accepting a permanent increase in vehicle curb weight at the highest center of gravity, reduced torsional stiffness, an elevated risk of spontaneous structural glass failure, and a system that guarantees water intrusion when routine maintenance is overlooked. Understanding the real physical, thermal, and mechanical trade-offs of panoramic glass is the only way to protect your vehicle from becoming another statistic in an industry-wide engineering compromise.